Almost made it to the finish line. You're almost to the very end of this course. And as a consequence, in this last lecture, we're going to try and pull things together. Wrap things up and take a high-level view at what have you done and where can you go next. And indeed, that's the first place we're going to start. We're going to try and pull together the key lessons we want you to take away from this course. The key ideas, the key topics, the things that you're going to keep with you as you move forward in thinking about how you use computational thinking to guide your own intellectual progression. And the second thing we're going to do is talk briefly about how you can build on what you've learned in this course to do different things. Both what additional courses might you take after this, but also how the things you've learned here should be of value to you in whatever endeavor is of most interest to you. So with that in mind, let's take a step back. And let's ask what seems like a pretty dumb question. What do computer scientists do? I suppose you could say, well, they compute. Of course, we've said something a little differently here. Remember what we've said. We said that they think computationally. What does that mean? Well, it says that a computer scientist has a particular mode of thought that they apply when they approach a problem. They use abstractions. They use the idea of breaking a problem down into pieces. Pieces that can be encapsulated so that we don't worry about the details inside, we just worry about the contract we have with that abstraction. I give it something, it does something, it gives me something back that satisfies that contract. We saw that they use algorithms. They have a particular way of breaking a problem down into mechanistic steps, detailing in order exactly how a mode of thinking should apply, how a computation should evolve, how a sequence of steps should be used in order to generate an answer to a problem. And of course, related to that is that notion of automated execution, that we can pass off to a special machine, an evaluator, the job of actually running through that sequence of steps once we've actually laid them out. So we've got abstractions, we've got algorithms, we've got automated execution. Computer scientists approach problems with that in mind. They think computationally. I'd like to argue that computational thinking is crucial, that it really is a fundamental or foundational skill that's going to be used by everybody in the world sometime soon. And you don't have to buy this particular version of computational thinking down here, but it's kind of nice. This mode of thinking, that really is what we want you to take away from this class. That's what a good computer scientist does. They approach a problem with a mode of thinking the same way a physicist, a biologist, a chemist, an economist would approach a problem, or a humanist, for that matter, with a different way of thinking. And that fundamental skill is going to be really important. So I'm going to suggest, in fact, using a very bad pun, that just like there are the 3 R's, reading, writing, and arithmetic from the last century, ubiquitous computing and computers are going to enable the spread of computational thinking as a fundamental skill for every well-educated citizen in the future. This is what we want you to take away from this class, is that there's now another piece of thinking, another way of approaching a problem that should be part of your armamentarium, your arsenal, your weaponry for tackling any kind of problem. That's what a computer scientist does. That's what we hope you're now set up to do as well. So, what is computational thinking? It's kind of a funny term, and we've used it a lot, but let's remind you of the steps associated with approaching a problem computationally. I've listed 7 here, and they really are the ones that you'd like to think about. You start, typically, when given a problem, by trying to identify or invent those useful abstractions. I'm going to remind you, what does it mean? It says, given a problem, I want to articulate, I want to identify the key elements inside of a problem, and I want to identify them in a particular way. That abstraction says, I'm going to describe a component. It's going to have a particular kind of behavior. Inside of that component, I or somebody else will build the details of it that will execute what that component should do. But the abstraction says that I can suppress details. I can bury information. And by suppressing the details, I say, I know how this thing works. Okay, a lot of words. What's a nice example? Well, one of the things we saw way back at the beginning of this course, the idea of something that takes a square root. That could be the very simple algorithm we showed you, but by building a module that computes square roots, I now have the abstraction of square root. I can say, I'll give any number to that module, and it'll give me back the square root of suppressed detail. We saw it with classes when we talked about object-oriented programming, where each class described a behavior. Within it, it had the mechanism to support that behavior, but I could think about it purely as an abstraction. Of course, associated with that idea of building the abstractions, I need to also articulate what are the interfaces between them. How do I relate things from one abstraction to another? What's the flow of information through this? But that's my first step. What are the abstractions? Note, by the way, that I may have to take multiple runs at this. I may build a set of abstractions for my first pass at solving a problem, and then in using it realize I didn't get it quite right, and I may either have to add another abstraction or refine the interface, if you like, to a particular abstraction. There's my first step. Identify the abstractions. Once I've got those abstractions, I want to then formulate a solution to the problem I'm challenged with as a computational experiment building on top of those abstractions. And the key word here is experiment, and the second key word is computational. I want to think about how can I use the tools I've built to try to find a solution to this problem, and I'm going to run an experiment to see if it does what I expected or not. So I'm going to use the abstractions to articulate or formulate that computational experiment. Having done that, I'm then going to design and construct a sufficiently efficient implementation of the experiment. Again, key word here is sufficiently, or words rather, sufficiently efficient. We've seen there can be many different ways to implement a particular algorithm, a particular computational structure. And what I want to do is try and find one that is as efficient as possible without having to take so much time to build it that I really lose out in whatever gain I might have in that efficiency. And we saw earlier in the course that we had different ways of reasoning about classes of efficiency. And we saw that there were standard tools, so that if I can reduce a problem to something I know how to do, like binary search, that's going to be a great way to build on top of something I know is an efficient algorithm. Once I've built that infrastructure, I need to validate it. And really what it means is I've got to debug it. I've got to run it, I've got to test it, I've got to test the units of it, I've got to test the integrated whole, I've got to make sure that it satisfies the different boundary conditions or special cases. I need to validate that this system is going to work. And then I run the experiment. I actually use the code to see if it gives me a solution to the problem I'm looking for. Calculating mortgage rates, finding an optimal problem or an optimal solution to a knapsack problem. Whatever the experiment is, I run it. And by the way here, associated with that is I need to evaluate the results of the experiment. We haven't talked as much about that in this course. We will in the follow-on to this course. But it's not just run the experiment. I need to make sure that the results I get make sense. They pass the laugh test, if you like. They really do capture what I would expect from this particular computation. And then I need to repeat it. I may need to go through this loop multiple times as I redefine or redesign what I'm actually using in my computational experiment, as my testing exposes places where things didn't work quite the way I wanted them to. That's what we've been talking about. There's computational thinking. That's one of the high-level messages we hope you take away from this class. Now, associated with that, there are a set of elements. And so let's look in a little bit more detail at what else we've learned in this course. So I'm going to suggest that there are 3 different A's for computational thinking. The first one, abstraction. I'm not going to say a lot more about this because you've really seen this throughout the course. But a key element of computational thinking is having good ways to design abstractions. That means understanding where the boundaries or separations are in a problem, where are the modules that naturally make sense. It's in operating in terms of multiple layers of abstraction, so that I may have abstractions that build on top of abstractions that build on top of abstractions, and I want to be able to think about all those at the same time. And of course, I don't just need the abstractions, I need the relationships between them. So abstraction is a tool that you're going to use a lot as you move forward. The second key tool is automation. How do I take those abstractions and mechanize them? I want to make sure that in fact they are set up mechanically to be easily executed, easily used. I want to make sure that that mechanization is possible. Just because we have some precise and exact notations and models, we want to make sure that we have something that can actually do the computation. And so we know that inside of the computer there is a machine that can interpret those notations. And that really says we need to make sure that we translate our abstractions into algorithmic solutions that we know are going to work well. And that, of course, is the last piece, and that's the algorithms. In some sense, that automation, that model of computation, defines what is computable And our algorithms then simply give us a language for describing that process and then for building abstractions on top of it. So we have abstractions, we have automation, and we have algorithms. And those are second level messages that I want you to take away from this class as you think about how you can use what you've learned in this class in other ways. Once we have this idea of computational thinking, we can think about how we might use it. And a couple of things that I think are valuable here, things that you've seen threaded throughout this course, are the following. The first one is, even if I have a computational approach to something, I can ask the question, how difficult is this problem? And how best can I solve it? We've already seen that theoretical computer science gives us a very precise meaning to these and associated questions and their answers. We've seen that certain problems have an intrinsic difficulty or a computational complexity to them. We've seen that some problems, and you'll see more of this in the future, have a fundamental difficulty that makes them very difficult to compute unless I use approximations to try and get around some of that difficulty. So computational thinking also has associated with it the idea that I know different classes of problem. I know different algorithms associated with those classes, and I can easily relate a problem to one of those classes as I think about it. And the second key example of computational thinking was to think recursively. That is, to take a problem and say, in order to solve this problem, can I reduce a solution to this problem to a solution to a smaller version of the same problem and some operations that I know how to use, or to a simpler version of a different problem and some operations I know how to use. Often a seemingly difficult problem can be tackled if I reduce it to something I've already solved, or I reduce it to a simpler version of the same problem. And we saw that notion of reduction and embedding and transformation constantly throughout the term. We saw the idea that to approach something like Towers of Hanoi, which looks like a really hard problem to solve, I could do it very simply, recursively, by saying, oh, if I know how to move a smaller tower, then the solution to a next larger problem is very simple. I've moved the smaller tower to the spare peg, I move the bottom disk, and then I move the smaller tower over. And of course, to move the smaller tower, I just keep reducing that until I get down to a problem that I can solve directly. This recursive approach to problems is very much a hallmark of a computer scientist's way of thinking. And it's a tool that's really valuable in many other problems. So, complexity and thinking recursively, two handy tools that you've seen. And of course, one can keep pushing this. And indeed, a fun way to think about this is, how might I keep reducing a problem to a simpler version of a problem, to a simpler version of a problem? And even if I do this fundamentally somewhere down here, or somewhere way down in here, there is a base case, a simplest version of the problem that I can solve. But this notion of reduction to simpler versions of the problem, that's a powerful tool, and that's part of what you want to do when you think about how to approach a problem from a computational perspective.